by the sea, shy yet proud. Hey, today we're going to be looking at capacitance and along with that capacitors, things that have capacitance. So what we can start just by thinking about is capacitors are things that store charge, okay? And a stored charge is going to generate, it's going to create for us this electric field in space. Now let's just think about one of the easiest ways that we could do this. If I have a parallel plate set up and I say, this is my high potential, this is my low potential, really it doesn't have to be positive or negatively charged, just high and low, then I know that my electric fields will run from high to low across it. It's a uniform electric field on the inside, meaning it's constant, and then I gotta be careful about these little edge effects, okay? That's what we know. Well, what we could really call this, instead of just saying these are parallel plates, this is a parallel plate capacitor, okay? This capacitor here has some capacitance. So because we have this positive and negative charge, or this high and low potential, and we have this electric field that has come into existence here, this stored charge and with this electric field separated by some distance, r, because, and that gives us the potential here. That's the potential difference. Remember, the potential is a field separated through some distance. This gives us this idea of a capacitance, okay? And what we can do with a setup like this is we could say that the charge stored on this capacitor is going to be equal to the capacitance of the system multiplied by the voltage across it, okay? And normally this voltage across it, it's supplied by some outside power source. So maybe you're hooked up to a battery or a wall outlet. Normally this is supplied via something, okay? This amount of charge, Q, is physically how much charge can you put on these parallel plates. What can you actually put on here? And the amount of charge that you could store onto this capacitor is entirely determined by the capacitance of the system, okay? It's entirely determined by the capacitance of the system. Now, this capacitance, if we wanted to, we could rewrite it as saying, the capacitance is equal to the amount of charge divided by the voltage, which would, kind of give you a unit of like coulombs per volts. But that's kind of a weird unit, so we're not going to use it. We're actually going to use a unit known as a farad, which is given by a capital F. This was named after Faraday, who did a lot of stuff within the world of electromagnetism, and we'll talk about later on in the year. But this C, it's a geometric property. Geometric. This capacitance, the ability to store charge, it's purely geometric in nature. And what this means is that it is defined by how you built the thing. Like physically with your hands, with your little robot arms or whatever, you had to build the capacitor. You had to build this thing. And that, right when you built it, determined what C is. Now we can give C like this. The capacitance C is equal to a kappa, we'll talk about that in a second, epsilon naught, we'll have to talk about that in a second too, multiplied by some cross-sectional area over, and up here I said this is some value r. Oftentimes with capacitors at least, we tend to use the symbol D. It just represents that separation distance between the plates, okay? And this is equal to the Q over V. Now, what are some of these terms here? Well, this K, this is what is known as the dielectric coefficient, and it's a constant. So right now, if we look at this parallel plate up here, we've got a metal plate, and there's air in between it, or a vacuum. Air might as well be a vacuum. But let's say in between them you stuffed it with, I don't know, a sponge. Well, a sponge is different for an electric field to move through than a vacuum is. And because the sponge has a different ability for the electric field to move through, we have to account for that down here with this dielectric constant, okay? So dielectric constant. There you go. Those are words. I'm good at that. This dielectric constant is actually modifying epsilon naught. Epsilon naught is the permeability of free space for an electric field. And all it represents is how easily can an E field propagate through free space. So a vacuum. Okay, that kappa modifies it because when I put a sponge in between our parallel plates, it's not free space anymore. It's sponge space or something like that. So the kappa is modifying this epsilon naught. Epsilon naught is a constant. We're not going to get into that constant right now. We often don't really need it, / it'll pop up later. Oftentimes we kind of ignore it. Well, we don't ignore it, but for what we do later on with the AP Physics C stuff, with the calculus-based things, we could sometimes just care less. A is the cross-sectional area. So if you have a parallel plate like this and then one behind it of the same shape, if we're looking like front on, that's the cross-sectional area there, okay? And it really stands for the area of overlap. So if you had a parallel plate and you built it poorly so that they didn't perfectly overlap, but they were like this, then actually the only region that's overlapping here is this. This region on the edge out here is not, because there's no green underneath it. This is not, and this isn't either. This would be our area in here that we could care about because there is overlap there. So that's what that means. And the D is just the separation distance between the plates that we have. Okay, so that is the idea of just like building a simple parallel plate capacitor and what some of those symbols and terminology means. Now, if we continue to think about this, if we are moving charges onto a capacitor, we have to do work in order to do that. So let's just draw the parallel plate again. Initially, this is uncharged. So when we put the first charge on it through our voltage source, the first charge goes on for free. And because this is positive, the other side generates a negative charge in the same way. But the next time we go to put a little charge on this, I have to fight through this potential, right? This positive charge is taking up electric space, and it's saying, hey, I don't want other positive charges near me. So when I bring a second one in, it's a little harder to do. And when I bring a third one in, it's even harder to do. And then it's even harder to do. And at some point in time, I don't have enough potential to actually do enough work to bring the last charge in. And that signifies that, hey, look, when we run out of this potential here, we can't bring any more charges into the system. Now, if we're doing work in this way, then what this means is that I can get work out of a capacitor. Work, if we remember, is equal to negative QV, where that V is a potential difference, and the negative deals in part with how we think about work and potential energies. So if you had a work of, and sometimes you'll see it in books written like this, if you just had QV, what this is representing, because there's no negative out in front, is this is representing that we, or something on the outside, did work. Okay, so something else is doing the work here. In this case, when it's negative, that means your actual system is doing the work. Now, when we kind of think about this, if we wanted to move the first charge, there was no work. As we continue to move charges, some work is being done, and that builds up that potential that we originally had. Okay, so whatever's supplying this potential, that is what will be built across this capacitor. So if you plugged it into a wall and it was at 120 volts in the wall, and assuming your capacitor didn't just immediately pop and it could store these charges, then this voltage would be the 120 volts. If you hooked it up to a 9-volt battery, it would charge up to 9 volts. Okay, now if we think about this in another way, we can think about this in terms of the work done as equaling the integral of the voltage by some tiny bits of charge that we're moving on it. And that looks kind of weird. So like, how did we get that? What were we thinking of there? Well, let's first just create this little graph. Okay? Imagine for a second that our graph is voltage with respect to charge. Kind of a weird looking graph. Like, why would I ever plot that? Well, if I plotted this, and I got this line out of it, then what this is really saying is this is saying if I take Q times V, aka this area underneath, what does that area represent? Well, that area is Q times V. What is Q times V? Q times V is a work, because we already knew that. We are geniuses. So this graph might look a little weird, but the area of it just represents the work being done, okay? Well, within the world of calculus, we know that this integral symbol represents the area, and if you're not familiar with this symbol, you'll get there at some point in time. We'll see it a whole bunch more throughout the year, especially when we start doing the AP Physics C stuff. But what this is essentially saying is that this is an area here. Now, what this means and how we can kind of think about this is, what is the area of this shape out here? Well, this shape that we drew is clearly a triangle. Ta-da! Which means that the work needed to kind of charge up this capacitor is based off of whatever this Q is out here. We'll call it capital Q as just being like, this is the value of the charge on the capacitor, whereas little q is some amount along the axis. So this is just Q, the base, times the height, which is V, right? And specifically, this is our, if we need to remember this is a final velocity, because down here at the base, this is the initial velocity. It's always a difference in potential. So what's the final velocity on this? Divided by, well, 2, because we've got a triangle. We cut the sandwich in half, okay? So that's just how we can start thinking about like how much work is done in moving charges into these scenarios. And that also gives us a really good idea of thinking about how much potential energy can we store in this capacitor, because if this is how much work it takes to charge this sucker, well, then that gives us an idea of the potential energy stored as well. We know that the potential energy that we store in the capacitor then is this, and I'm going to pull the 2 outside, is this 1/2 QV, and I could actually rewrite this in a few different ways. If we think back to the idea that the charge stored on the capacitor is the capacitance multiplied by the voltage, and we do some substitutions into this equation, we actually get 2 more ways to write this. We could write this as 1/2 CV squared, or if we wanted to, we could write this as Q squared over 2C. So all of these are ways to think about the amount of energy stored within the capacitor, because we are taking charges and we're putting them on the edge of that E field in this way, okay? And through this little graph here, this is a super helpful thing just to start thinking about, you know, how are we actually doing work on this, and that idea of the work gives us that stored potential energy. Okay, so this is a kind of neat thing, and really, you know, whenever I wrote this out, we're just thinking about the magnitude of the charge on this, or the magnitude of the potential. We're storing that in the capacitor, and that's kind of what matters for that there. Okay, if we wanted to, and this is something that we don't see a whole bunch, we can think of this as, can we use the potential energy stored? Can we do this for an E field as well? And we can. If we start with this equation, 1/2 CV squared, this we could say is equal to 1/2, and then let's take this capacitance here and let's expand it into the geometric property we had before. So that would be our kappa epsilon naught A over D, right? And then here is a voltage squared. Well, I know that a voltage is given to us by an electric field through some sort of distance, and normally we write this as R, but we could write it as D if we wanted to. So this would be like saying ED squared. And this right here allows us to say, hey, look, even if I don't know, as long as I know what my capacitor is doing here, I can also write this in terms of the electric field, okay? We really don't use this one. That will like hardly ever pop up because this right here is really just the capacitance, so why would you write it like this? But if you needed it for some reason, you could, okay? So that's everything in regards to basic ideas about capacitance and capacitors and what we're thinking about here. all the way from the units of farads to the equation to describe them, how they're set up geometrically, and what we can do with work and energy to get that. We're going to look at in the next few videos are some examples on, how much charge can we store on them, how much work can we get out of them, what's going on with that. So make sure you check out those next videos and see what's going on with capacitors in a little bit more detail. But until then, this is finished. Take it easy and adios.